Hello everyone, this is the presentation of my watermark image algorithm. I made a new digital image watermark algorithm. About watermarks, the prompts are marketing and thief protection. You can sign your name into the image so everyone should know this is your image. And with the watermarks, others can't be able to download the image or use it without your permission. About the cons, it may distracting the original image. Once you insert the watermarks, the image may be changed a little to the original image. About the existing watermark algorithm, someone use DCT or DWT or SVD. This is to transform our image into matrix. Like this, he used SVD to do the watermark algorithm. And someone performs in multiple subbands. We perform only in one subband. And someone use different embedding methods. Like this man, and he inserts his watermark in two subbands, HL and LH. And this is the Cox embedding algorithm. He invents a new embedding algorithm. And people use different encryption methods. About our watermark algorithm, we use DCT and DWT to transform our image into matrix. About the encryption algorithm, we use chaotic encryption algorithm and anode encryption algorithm. And about embedding algorithm, we use Cox embedding algorithm. This is the DCT code we use in MATLAB. It can transform our original image matrix A to matrix B. This is the DWT. It can decompose our image matrix into 4 subbands. And once you perform it in one subband, it can decompose this subband into smaller subbands. This is the MATLAB code we use. About the anode encryption algorithm, this is the anode cat map. You see, after 300 times transformation, the image returns to the original image. So our idea is we perform n times anode transformation at the embedding, and at the extraction, we perform the period minus n times anode transformation. So we can get the image similar to the original image. About the chaotic encryption algorithm, we first use keys to generate a chaos sequence, and we use the reshape in MATLAB to reshape it into a matrix. And we do mathematic process like this to encrypt our matrix. In the decryption, we use encrypted matrix and the same chaos matrix and do mathematic process, and then we get the recovered matrix. About Cox embedding algorithm, this is the code we use. The strands we use about 15.6. Assume this is our watermarks. It is 32 lines, 32 rows. And we should insert it into our one subband. Let's say it's 108, 128, 128. So we insert every pixel into the blocks. So each block is 4. We insert one pixel into this 4 block. And the position where to insert, we can use a key to determine it. Let's say we insert the pixel into row 3, column 2. This is the procedure of our algorithm. First, we perform watermark. We use watermark and perform encryption algorithm to encrypt it. And then we perform two-level DWT to host the image and get our subbands. Then we perform DCT to the subbands and the encrypted watermarks. And we use embedding algorithm to embed the encrypted watermarks into the subbands. And then we use IDCT and IDWT so we can get our watermarked host image. And about extraction, we get the watermarked host image, and then we use two-level DWT followed by DCT to get our matrix, and then we decide which data we should extract the user key to get the encrypted watermarks, and we decrypted it into our recovered watermark. This is a simulation result. This is the host image, a watermarked host image, and this is a recovered watermark. This is processed with JPEG compression, and this 3 is Gauss noise. This 3 is salt and pepper noise. This is through a media filter. This is cut part of the image. This is through skull. We first get it to 0.5 smaller than our original image, and then get it 2 times larger than it. So it is the original size, but it lost some information. This is the date. This part is our simulate date, and this part is what we get from our reference 7. We can see our PSNR in the proposed algorithm. The proposed algorithm is two-level DWT in LL subbands. When the PSNR is larger than 35, we can't tell the difference between two images. Although it's lower than 35, but we see it's very similar with the original image. This is the host image and the watermarked host image PSNR. And this date is the normalized correlation between watermark and recovered watermark. We see the date in our proposed algorithm is much better than reference 5 and 6. You see it's much larger than him. And about the reference 7, in the Gauss noise, we performed a little bit less than him. And in the salt and pepper noise, we perform better than him. You see this. And about the filter cutting and the skull, we perform less than him. This is the performance. The yellow line is our proposed algorithm. You see it's higher than this red one and this blue one. In the Gauss noise, the gray is higher than yellow, and in the salt and pepper, the yellow is higher than gray, and about the median filter, the cutting and the gray is higher than a little bit higher than yellow. The conclusion is I think my algorithm is successful. It's just a little bit worse than reference 7, but much better than reference 5 and reference 6. And the best choice for us is to perform an LL subband. We see this is the date in different subbands, and LL the date is much better than the other three subbands. This is because LL contains the most energy of the original image, and the other three subbands they are easy to be affected by noise. And about the extended work, we can insert our watermark into different subband and multiple subbands, and like we can explore. We divide our watermark into different dates and explore which date should be inserted into which subband, and then we may get a better performance. That's all.